Dear student, today we are going to design the Hartley oscillator using op-amp, and simulation is also done by NI-Multisim software. So, as you know, the Hartley oscillator is the LC oscillator in which the frequency of oscillation is also depends on the value of inductor L and capacitor C. So, in this video, we are going to discuss about the theory of the Hartley oscillator as well. The design procedure we will also discuss, and then the example to design the Hartley oscillator and the simulation using NI-Multisim software. So the basic work, this is the basic working of Hartley oscillator using op-amp IC. So the Hartley oscillator is the sinusoidal oscillator. So it produces the sine waveform at the output, and it is a LC oscillator in which the oscillation frequency is determined by a tuned circuit that is consisting of the inductor L and the capacitor C. The circuit was invented in 1915 by American engineer Ralph Hartley. So this circuit is useful for producing good quality sine wave signals in the RF range. So here the RF ranges are from 20 kilohertz to 30 megahertz. So this oscillator uses an LC tuned circuit, or we can say tank circuit, to control the oscillator frequency. The personal feature of this oscillator is that the tank circuit consisting of a single capacitor in parallel with two inductor are in series, or a single tapped inductor, and the feedback signal needed for oscillation is taken from the center connection of the two inductors. So here the main advantage of Hartley oscillator using op-amp IC is the gain can be individually adjusted using the feedback register RF and the input register R1. So here you can adjust the gain using the these two registers RF and R1, and therefore the gain of the circuit is less dependent on the circuit elements of the tank circuit. So this increases the stability of the oscillator in terms of its frequency. So you can design the Hartley oscillator using op-amp. It provides the better gain and stability. So you can also design the Hartley oscillator using FET and using transistor, etc. So this is the Therefore, the gain of the circuit is less dependent on the circuit element of the tank circuit, and this increases the stability of the oscillator in terms of its frequency. This oscillator uses two inductive coils in series with a parallel capacitor to form its resonance circuit, tank circuit, that is producing a sinusoidal oscillations. So the resonant frequency of oscillations is given by F naught is equal to 1 upon 2 pi root under L equivalent into C. So you can find out the value of the oscillation frequency by using this formula. So if you want to design the Hartley oscillator on some particular frequency, so you can find out the values using this formula, and this is the uh, uh, circuit of the Hartley oscillator using op-amp. So here this is the op-amp IC. Here we are using the 741 op-amp IC, but you can use the other general purpose op-amp ICs, or you can design the high speed ICs with the help of high speed ICs. So here using you can design 741 IC, So this is your general purpose op-amp IC, and here these are the two inputs, inverting and non-inverting, and this non-inverting is grounded over here, and this is your inverting mode, and at this mode R1 and RF is connected over here, and the feedback path is also connected. So these this is your tank circuitry. It consists of L1, L2 and the capacitor C, and this is the oscillate final. You can find out the result with the help of CRO. So this is your CRO. You can find out the result on CRO, and this is the design procedure. So how to design the Hartley oscillator using op-amp. So here the design steps are also given over here. The first one step is you can assume the value of oscillation frequency f naught. So if you want to design the Hartley oscillator on some particular frequency, so you can choose the value of that frequency and you can design the Hartley oscillator for particular application. So the formula is f naught is equal to 1 upon 2 pi root under L equivalent into C, and here L equivalent is also equal to L1 plus L2. Now the second step is choose the value of inductor L1 and L2. So you can choose the value of inductors, and the next step is calculate the value of inductor using C. So you can calculate the value of C using this formula, that is C is equal to 1 upon 4 pi square F naught square into L1 plus L2. So here using this these three design steps, you can design the Hartley oscillator. Now consider this example. Here the example is given over here. Design the Hartley oscillator for frequency f naught is equal to 9.18 kilohertz, and L1 is equal to 2 millihenry and L2 is equal to 1 millihenry. Then calculate the value of capacitor C. So if the frequency is given over here, then you can find out the value of capacitor C, or if the value of components are given over here, suppose, then you can find out the frequency also. So using this formula you can calculate the value of components. So here, because f naught is given over here 9.18 kilohertz, so the first, according to our design step, first choose the oscillation frequency, that is 9.18 kilohertz, and the second step is choose the value of inductor L1 and L2. So the inductor values are given over here, 2 millihenry and 1 millihenry. So the value of inductors are L1 and L2 is equal to 2 millihenry and 1 millihenry. And next one step is calculate the capacitor C. So the value of capacitor C is calculated using this formula. So the C is equal to 1 upon 4 pi square F naught square into L1 plus L2. So here F naught is given, already given over here, 9.18 kilohertz. So this is 9.18 kilohertz, and then the L1 plus L2 is equal to 3. 2 plus 1 is equal to 3, and this is given in millihenry, so it will become 3 into 10 raised to power minus 3. So after calculating, the value of C will be equal to 0.1 microfarad. And now the last one step is, if the R1 and RF is not given, then you can assume the value of R1 and RF, and here you can choose the R1 is equal to 100 ohm and the R1 is equal to 100 ohm and RF is equal to 1 kilo ohm. So according to this example, you can design the Hartley oscillator, and simulation is also done by the NI-Multisim software. So let's design the circuitry using NI-Multisim. So here this is the OPAMP 741 IC. You can choose it and drag it. Now collect all the components like this. Here you can choose the capacitor and resistors also. So here this is your resistor, or you can choose the potentiometer also. This is variable resistor, and this is the simple resistor R. Next, the inductor is also required in the circuitry. So this is the inductor, and the one more inductor is required. So select the inductor and drag it onto the workspace, and the capacitor is also required over here. So you can choose the capacitor. Here the power supply is also required. So plus VCC and minus VEE is required. So select the plus VCC and minus VEE and drag it. Next, the ground terminals are also required. So select and drag it. Now, all the components you can select like this. And next step is assemble the circuitry. So here you can connect all the components. Now you can flip the circuit vertically. So you can rotate the component also according to your design procedure. Now connect all the components. So here you can rotate the variable register like this, and connect the register R1 and adjust the position of the components, and connect this register to the inverting mode, and the feedback register is also connected like this. And here this is your pin number 7. It is used for plus VCC, and 4 is used for minus VEE. So connect the pin number 4 to minus VEE, and this is your inductor L1 and L2. So these are inductor L1, L2 and C forms a tank circuit. So here connect these inductors like this, and the capacitor is also connect over here, and you can connect the L1 and L2 like this. And here this is your non-inverting terminal. So connect this non-inverting terminal of op-amp to in between L1 and L2, and this is your plus VCC supply. Here the plus VCC is you can also change the value of the components. So here adjust the L1 and L2 position of the L1 and L2, and adjust the positions also like this. So you can adjust the position if the connections are not properly connected. Then you can also delete or again connect it. So this is your, you can delete if the connections are not proper, then the option is you can delete the connections. And here the CRO is also required to check the output. So select the CRO. Here all the instruments are given over here. So this is your CRO, and the output of the op-amp IC, that is 6 at pin number 6. So you can connect this pin number 6 to CRO, and the other one channel of the CRO is grounded. And here this is your L2 is connected to the pin number C. This is C1. Connect this terminal to according to this procedure. And this is R2. This register is also connected to the L1, and C1 is also connected to the L1. Now the connections are ready. Connect this feedback register to the output pin of at 6 of op amp. You can also adjust the position of the components. And here, if you, so now the connections are ready. And now according to our design example, you can change the value of the components. So in our design, the resistance are, the R1 is 100 ohm, and RF is the variable resistor. And you can also change the label. So you can change the label like RF, and this is your register R1. So you can change the label, and this is your R1. Now change the value of the supply voltages. This is 15 volt, and the minus V is also required over here, 15 volt. So change the value of the supply voltages, plus 15 and minus 15 volt. Now change the value of the inductor according to our design example. So the L1 is given over here 2 millihenry, and L2 is 1 millihenry. So we can change the L1 and L2, and the capacitor is 0.1 microfarad. So now we are ready to simulate our circuitry. So our circuitry is ready. Now simulate it by the run button. And as you can see over here, because the output is required in AC form, so you can adjust the AC. And now after changing the scale of channel A and time base like this, we can find out the output result with proper waveform. So you can change the scale, and after adjusting, you can find out the proper waveform. So change the scale also, and no results. So here you can change the scale continuously, and after changing the scale, So here, as you can see over here, this is your perfect output result in sine waveform without any distortion. So you can design the Hartley oscillator using NI-Multisim software with proper sine wave output waveform. Thank you for watching.